Then we'll cover a few minutes on providing you some information on how you can use generative technology today within Fusion 360. And then we'll spend the majority of the presentation covering a sample project from start to finish so you can see the entire workflow. Then at the end, we'll save about 10 to 15 minutes for closing, provide you some information on how you can get some added resources later on. And then we will have time for a live Q&A at the end as well. So prior to kicking off, I'd like to launch our first poll question of the day, and you should be seeing this come across. It's what is your current level of experience with generative technology? And that can range from none to advanced. We'll wait a few more seconds here as people are continuing to answer. And it looks like the majority of people are pretty new to generative, which is great and certainly understandable. We only launched generative technology within Fusion about 5 or 6 months ago, so it is still pretty new technology. So again, thank you for everyone that answered that poll. So first, I wanted to cover an introduction to generative technology and talk about what it really means for the entire industry. So for those of you that are familiar with Autodesk has been making CAD software, computer-aided modeling software for at least 35 years at this point. And when you think about the process of using conventional CAD, there's really not much that's computer-aided about it, right? So it's an engineer who has to put their ideas into a program to meet the conventional requirements that we've always had for manufacturing or for our product ideas. So as we look towards the future, and as we look at the growth of additive manufacturing, cloud computing, 5-axis CNC, we need a brand new set of tools that allow us to leverage all of this kind of technology. So rather than the engineer creating just the CAD and just the product itself, we really want the engineer creating the objectives and the higher level requirements for their project to then explore a wider range of hopefully higher performing options. So the general process that we're really trying to affect is something that we've heard from a lot of our customers, is that typically only a small handful of concepts are really looked at within a product cycle. So maybe 4 or 5, like you could see on the screen. And then those concepts are evaluated for their structural integrity. You need to make sure they're strong enough. You check for manufacturability. And throughout this process, you're not really exploring a range of options. You're typically exploring a small handful of options that are close to what you might have manufactured in the past. And in the end, you might be bringing a product to market that took longer than you would have hoped. And it might be compromised for some of the manufacturing process because you haven't explored a wider range of options. So where we really see generative fitting is at phase 1 within your product cycle. So rather than taking a small handful of concepts, the idea is you lead with your requirements for a project and you generate hundreds or thousands of validated manufacturable options as step 1 within your process. So this is really just taking opinion out of the process that you typically had in the past. So the goal here is to allow you to explore those options quickly, hopefully select one that is higher performing. Ultimately, this will allow you to bring a higher performing product to market quicker, typically with material and manufacturing options that you might not have explored in the past. So when you're looking at applying generative technology within Fusion, the main advantages that you're looking for, again, is that idea about exploring a range of options. So there are a lot of optimization softwares that are out there that allow you to take one set of inputs and yield one specific output. The idea that we're really looking at is to explore a range of options. So if you put in your requirements for a project, rather than just one specific output, you can explore hundreds and thousands of outputs that allow you to make trade-offs on materials, performance, and manufacturing types. Second to that would be, with the growth of additive manufacturing, we know that we need a new set of solutions that allow us to think in this way. So as we start looking at additive manufacturing, generative is is a great way to put in our requirements for that process and then start to generate options that, again, we probably wouldn't have thought of since we're not too familiar with all of the complexity that additive can really produce yet. It's also important to note that this is not just exclusive to additive manufacturing. So generative can also be used for subtractive manufacturing and conventional manufacturing, which is something we'll talk about later. And then finally, parts consolidation. So this is a story we'll talk about later as well. It's the idea that you can take what used to be 10, 15, 20 components and reduce your supply chain to generate a single component that could replace all of those. So the first example that I'd like to show today, and many people might be familiar with this, is the General Motors generative story. So GM took that seat bracket assembly that you see on the top left, and they looked at, what does this seat bracket need to connect to? What does it need to avoid? And what are the loading conditions that someone might expect within the seat bracket? So they took that and they started to generate options that could consolidate that assembly from 8 components to 1. That consolidated assembly would be 40% lighter than what they've worked with in the past, and also 20% stronger. And probably more importantly than any of those other things is that they generated 150 viable, validated options that they could then explore and make trade-offs for later on. So just to see a little bit about how this process works. So generative takes the entire volume that our geometry could fill, and it either adds or subtracts material away from that to get to a final solution that's validated. So again, if you can see from the screen, it's much more than just optimizing for one solution. It's optimizing for hundreds or thousands of solutions, comparing materials and performances that you might not have in the past. So as you start looking at how to apply generative technology to projects you might have, the first thing you always have to do is take it within the context of the assembly. So here, GM took their conventionally produced seat bracket, and again, they looked at what are the connection points we need to keep, what are the assembly features that we need to avoid, and then from there, they were able to generate options to then replace that assembly with. So while many times we talk about the aerospace industry, automotive research as kind of the main drivers, I think it's really important to note that some of the key successes that we've seen for our customers within generative technology happens within heavy equipment, machinery applications, right? So one of these that I'd like to highlight as well, and this is completely unique from what we've just shown with GM, is the story of Claudius Peters. So Claudius Peters is a manufacturer of what's called clinker coolers. These are cement production machines that are probably the size of a football field. So they're not looking at additive manufacturing yet for a lot of their products. They make very heavy-duty manufacturing equipment. So what they use, and what's really unique about this, is they use generative at the front end of their cycle to kind of take the opinion out of that early phase. So they knew the loading that their parts had to adhere to. They knew some of the manufacturing types that they might want to explore. And then using that, if you see the final point on this slide, the main advantage is that they're breaking down the silos from all of these groups that used to be separate. So it used to be there'd be someone on a product team that would create a model. They would send that to the engineering team. The engineering team might send it back. They'd create a model. The manufacturing team might send it back as well. And that process continues. So at least if you start with phase 1 as generative, you know that it's structurally viable for what you need, and that the manufacturing types are at least valid for additive and or subtract. So as we look a little bit about how this process works, and this is what we'll be covering today with that hands-on example, is the only thing that we need to do to set up our project is we need to show what you currently have on the screen here as preserved geometries, and these are key pins. So we're saying after the generated solve, I know that I need material within all of these sections. We then need to set our objectives. So what are we actually trying to achieve within this process? We then need to set our manufacturing types. So we can set specifics for the additive manufacturing, subtractive manufacturing process as well. We then need to set a range of materials. So with this idea about exploring options within this process, we've talked about the idea that we want to just be looking at more than one material or more than one performance characteristic. Here we can put up to 10 materials that we can solve for at the same time. So again, we can start exploring trade-offs that we might not have in the past. And then after those 4 or 5 options, that's the only thing that you need to get started. And then you can start to explore all of those options. So if I fast forward a little bit to start seeing some of the results, you can see it comes up with these very organic generated geometry. The more organic ones are being solved for an unrestricted manufacturing type, meaning it's just providing the ultimate solution. The additive ones will look a little less organic, and the subtractive ones will look almost prismatic. From here, they could take back the one that they thought would provide them with the highest performance, and that's what you can see on the screen. And what's really valuable here, again, Claudius Peters is not using additive manufacturing. They're using conventional welding. So what they did is they took the generated geometry really as an inspiration for their process as phase one to then model something that could be conventionally manufactured on top of it. So again, I think there's always this concept that generative needs to have additive manufacturing. However, there's lots of other opportunities that we have to explore conventional manufacturing here as well. So I'll fast forward in this video slightly and you can see the final modeled component there. So the generated component on the left and using that as the inspiration for the final modeled component there that you're seeing on the screen. So when you're looking at how to apply generative, again, the great places to do it are when you're working on a new project from scratch. So you can use this, like we showed with Claudius Peters, as a guide to then model from. You can use it to identify which materials that you'd like to work with. Or if you're using something like additive or 3 and 5 axis subtractive, you can generate the actual model itself. Second would be parts consolidation. So we talked about GM and how they took a assembly of 10 to 15 parts and then generated that down to 1. So you can also look at how you can consolidate entire assemblies using this process. And then finally, part enhancement. So if there's parts that you have out in the field that you're currently selling or currently producing, you can look at ways that you can enhance existing components that you might already make to look at new materials and new performance options. So finally, as we kind of close out the introduction, so what's unique about generative? First is that it's a manufacturing aware technology. So when we're generating options that we know are ready for additive and subtractive. Second would be we're exploring a range of options. So we're looking at tens, hundreds, or thousands of higher performing options right in phase one of your product cycle. We're looking at multiple materials. And then finally, this is something that we didn't cover too much, but we'll show later on, is that the generated output CAD geometry that you're creating is usable solid CAD. So we're not just optimizing for a mesh, it's generating solid CAD geometry that we can continue to work with. So prior to moving on to this next phase, I'd like to launch our second poll question of the day. So which one of these personas matches your role the closest? And we'll leave this open for just a few more seconds. And closing it now. So it looks like we have a pretty good mix of everyone. The majority of people say that they do everything, which is great. A lot of engineers too. And that's kind of, I think, the important part of this, right? We talked about how this is breaking down the silos between all of these separate groups. So there's a value within the generative process that can be found within each one of the personas that we talked about in that poll question. So thank you for everyone that answered that. Okay, so moving forward, I just wanted to spend a couple minutes talking about how you can get started using generative technology yourself. So generative used to be only available to Fusion Ultimate subscriptions, but now generative is available to any commercial Fusion license. So the key point there is commercial. It runs on a cloud consumption model, which is 25 cloud credits to generate those hundreds of options that we talked about, and then 100 cloud credits to output one of those solid CAD models. So we'll talk a little bit later about what that means. So the other thing that's really important to note is that you can also use a free trial license, a free commercial trial license to get started using generative technology. So this will provide you with a 30-day trial of a commercial Fusion license and about 300 cloud credits, which is enough to do a couple projects. So I'd highly recommend, if you want to take a look at how to try generative on a couple different, this link that I'll share at the end. Then as you're looking to learn how to use generative, um, there's a Fusion adoption portal, which has a lot of training and content to help you get started with Fusion in general, so anything from CAM to simulation. It also has a generative chapter that I think is really useful. So it's about 30 minutes to an hour, and it really walks through pretty much everything you need to know to be successful using the technology. So I'll share that link at the end as well. And then finally, I talked about how my job is to make sure that our customers are successful adopting generative technology. If you have any questions, please feel free to reach out to me. So if you have questions on what projects might be the most successful, how do you get started, please feel free to reach out to my email address that's on the screen here. Okay, and moving forward for the majority of the rest of the presentation, we'll be covering a sample project, the entire workflow. And prior to doing that, I wanted to launch our last poll question of the day. So this is out of the values of generative that we talked about today, which one of these would provide the most value to you and your business? Okay, we'll leave this open for just another second as people are still answering. Thank you for everyone that answered the poll question. It looks like the majority of people are really interested in trying to increase their innovation capacity, so possibly exploring options that they wouldn't have in the past. And then second to that would be accelerating product development and then planning for additive manufacturing. So once again, thank you for everyone that answered the poll question today. Okay, so moving forward, the first project that we'll be looking at is the GE jet engine bracket. So this is a project that many people might be familiar with, and it's something that GE ran about 5 years ago to see what a community of engineers could produce for a conventionally produced part that they made. So it's that jet engine bracket that you see on the bottom right. And this kind of feeds in with everything that we've been talking today, that there's more than one right answer to any engineering problem. So the community of engineers, and there were hundreds, if not thousands of results for this, came up with all of those unique solutions that you see towards the lower right-hand side of the screen. Each one having their own unique advantages. Some might be lighter but more expensive, be stronger. Some might be ready for metal additive manufacturing. And this is exactly what we're trying to do within generative technology, is take the requirements and then let you explore the options effectively. So the first thing you have to do, and this works for any generative project that you have, is that you first need to understand your functional and your manufacturing requirements. So what are the loading conditions that your generated part needs to handle? What are the forces? Where does it need to be constrained? Second would be to set up the geometry. So we talked about this a little bit, but we need to understand what are the critical points that we need to connect to, which we call preserved geometries, and what are the geometries that we need to avoid, and we call that obstacle geometries. Third would be, how do we explore and then find the right ones and make those trade-offs that we've talked about? So this is the same workflow that we'll show here, but it's the same as any other project that you would work on. So for the GE bracket itself, they provided all this information to the community. So they were looking at a titanium material that had additive manufacturing requirements, that had a factor of safety, and then all of those loading conditions that you see on the lower left-hand side of the screen. So this is what we'll be walking through on how to set up this problem. So again, the first thing that we need to know, now that we set up our functional requirements, we know those loading conditions, is we need to set up our geometry space. So on the lower left-hand side of the screen, you can see what's called preserved geometries. You can think about that as a keep-in. So that's after this final solve, we know we need material in those sections. And then you have obstacle geometry, and you can think of that as a keep out. So after generating, we know that we can't have any geometry that's extending into those areas. So with that, we can get started with generative in Fusion 360. So for those that aren't familiar with Fusion 360, Fusion is a CAD, CAM, simulation, and now generative package that's all cloud connected. So you can see at the top, when I click on this workspace dropdown, you can be in the modeling environment that we are currently. You can validate your models here with FEA. You could create CNC tool paths and eventually additive manufacturing here as well. And what we'll really be focusing on today is that generative technology workspace here at the top. So the first thing that we would do is we take this existing bracket, the one that they've always produced, and we click on the drop down and go to generative technology. So the first thing you'll notice is we now have a new user interface that helps us walk through this process that we've talked about so far. So everything in Fusion is meant to work from left to right. So the first thing we'd look at is editing a model. This is creating those geometry sections that we've talked about. The second would be calling those geometry sections out. So we've talked about calling out preserved geometries for keep in and obstacle geometries for keep outs. We'll set up our loading conditions, so our forces and our constraints. We'll set our objectives on what we're trying to solve for and our manufacturing types. Then we'll apply a range of materials to solve with, and then we can go ahead and start solving this problem. So again, the first thing that we typically do is go to this edit model workspace where we can start to extract some of those preserved geometries that we know that we need. So here, the first thing that I might do is I might make a copy of this component so we can use this later to extract some of those geometries from. So the first thing that I might look at is creating those pins. So if we create a sketch on this lower face, and again, this is just one of a couple different ways to do this. I can start creating these features all across the lower face of this part, and then I'll press the E key, which is typically for extrude, but rather than extruding from this part, I'm clicking on the operation, and I'm just going to go with the intersect command. So what that does is that's essentially just extracting the geometry away. So it's not cutting it, it's not creating a new solid in that space. It's taking one of those geometries that we've copied and just extracting those pins that we know that we need. So after doing that, I can press OK, and you can see pretty quickly we have that geometry and then all of those solids that we've extracted from it. So now I can go ahead and hide the initial geometry. And we also know that this bracket needs to attach to a plate. So we need to create that geometry ourselves. So in this case, we can just select one of the faces, create a box, drag that down each time, making sure it's a new solid so we can call it out effectively later. Now we have the plate that we can avoid at the bottom, and then the pins for the preserved geometries at the top. The next thing we need to think about is we also need to really fully understand that we need to call out the inside of where the bolts need to be placed as an obstacle geometry. So in this sense, we almost need to create the absence of geometry within our final model here, so we can call that out. So in this sense, I can go ahead and hide this plate for now. And we want to call out the inside geometry of each one of these faces. And then we also want to make sure that we have enough clearance within our assembly to actually reach that later on. So what I would do, and this is just one way to do this, is I might patch each one of the surfaces. So again, this is using some surfacing tools within Fusion. So creating a patch on each one of those faces. Then from here, I can go back to the solid tab. And in this case, we're just going to do an internal fluid volume. And what that does is that essentially just extracts all of the geometry on the inside of all of those faces and creates that as solid CAD for us. So now if we highlight that, you can see that we've quickly created all of those regions and we still have our plate there. So the next thing we need to really look at is what are the assembly clearances that we need to meet? So we can't just call out the inside of all of those faces to have a bolt there later on. We also need to know that we have the assembly clearance to reach those, to reach all of those geometries. So what we could do in this case is just take the top surface from each one of those and extend this up a certain amount, so we know that after we've generated the geometry and we have our solid part, that there's nothing blocking the assembly process of actually applying the bolt within those faces. So we can choose to join that. And then in the end, we have our pins at the bottom. We have our plate that we know we need to avoid. And then we also have the internal geometry of where a bolt needs to get placed, and then the assembly clearance to actually get there. So we'll fast forward this a little bit. So currently we've created all of the geometry that you see on the bottom. So we've created these pins and we've created the obstacles that go through them. We would just need to do that on the top as well, but it's a very similar process where we can run the intersection through that part, extract the geometry and move forward. So since we do have a lot to cover, I am going to skip through that part a little bit. So in the end, we come out with a solution like this. So again, we have the constant wall thickness around those pins, we have the plate to avoid, and then we have all this geometry at the top. So working from left to right, the first thing that we do is we call out our preserved geometries. So clicking on that green tab at the top, we can start selecting the bodies that we know that we need to keep in within our final solve. So after I do that, all of those will turn to green. We can then move on to obstacles. So if I hide my preserves, it's showing everything else. I can select the obstacle command, drag and select all of those objects, and now all of these will turn to red. So again, we have our preserved geometries in green, saying what our keep ins are, and we have our obstacle geometry in red, saying what it is that we need to avoid. So moving forward, the next thing that we need to do is start to apply our loading conditions. So for this, loads can only be applied to preserve geometry where we know there is going to be CAD at the end of the solve. So we can just go ahead and hide the obstacle and we can start applying our load conditions. So this is something that was told to us within this project, and it's going to be unique to each project that you work on as well. So we're constraining the inside faces of the bolt locations, and then we can start applying a load to the inside faces for the clevis pin at the top. So in this one, it has a positive load of 8,000 pounds in the Z orientation. So you can see after we've done that, the arrows are pointing up for that load case 1. And we also have that lock showing that we have a fixed constraint within each one of the pins. From there, we have 3 other load cases to add. So to speed it up a little bit, we know the constraints are the same for each one of them. So we'll clone load case 1 to then activate load case 2. In this one, we know that there's a horizontal force at negative 8,500. So we'll put 0 for the Z, and we'll put negative 8,500 in the Y. And now you can see, rather than those force application arrows pointing up, they're pointing horizontally out in this case. We'll clone that one more time, and we'll follow the same process. We'll keep the constraints the same, and we'll apply a force of negative 7,060 in the Y, and then positive 6,357 in the Z. So that's providing you that force application that's at an angle. You can also apply it with an angle rather than breaking it up into the vector components like I did. And then the final loading condition, we'll clone this one more time to keep the constraints the same, and we'll only adjust the force. In this case, we had a torque that needs to be applied through the center of this clevis pin, so we'll select one of the faces. And in this one, we can do 1400 in the Y. And then we'll do the opposite on the other face. So here we'll do minus 1400. So now you can see that we have one arrow pointing in one direction and then the other pointing in the other direction, sort of applying that moment that we talked about. Okay, so now we have all of our loading conditions set up, and we have all of our geometry correctly set up as well. Again, moving from left to right, the next thing that we would do is apply our objectives. So here we can say if we'd like to minimize mass with a specific factor of safety, or we can try to reach a mass target specifically and say, I need all parts to be 1.5 pounds, again, reaching a specific factor of safety. So in this case, we'll choose to minimize mass while achieving a factor of safety of 1.2. Next, and this is probably the one that's been most exciting for a lot of customers, is applying manufacturing intelligence. So here, if we go to the next icon, you'll see a manufacturing dropdown. And here you'll see a couple different things. The first is you can select unrestricted. That's essentially saying, generate me the perfect part without even thinking about manufacturing. And that's typically really helpful if you're looking at using a generated output as an overlay for a more conventional CAD model on top of it. Second would be additive manufacturing. So when you check this, it will enable a setting for a maximum overhang angle and then a minimum feature size. It's also important to note that within additive, it's providing you with 3 specific outputs. So what you get in the end is something that could be self-supporting in the X, the Y, and the Z orientation. And then finally, we have our milling constraints. So for subtractive manufacturing, and this is something that's new about 2 or 3 months ago, we have the ability to select a series of 3 or 5 axis subtractive configurations, and then the tooling orientations that we'd like to look at. So for this one, we might say I'd like to look at a configuration for 3 axis subtractive manufacturing that's milling against the minus Z orientation. I have a minimum tool size here and a shoulder length. And then we can add another one. So we'll say this next one, we'd like 5 axis. Maybe we'd like to look at a smaller minimum tool size here. Same thing, we could do another one with 3 axis, but this time we'll vary the milling orientations that we'd like to look at. And again, here the idea is we want to explore a range of options. So we do want to put all of these in so we can try to get something unique. And then finally, for the last phase before finishing the setup, we want to select our materials. So again, this kind of follows the same idea that we've talked about throughout, is that the entire point of this solution is to explore options that you might not have thought of in the past. So if you conventionally manufacture something with one material, you have the ability to try up to 10 specific materials here. So again, exploring something that you might not have thought of. So here we're selecting a couple different types of aluminum. We could select steels, titanium, again, materials that we might not have thought of producing a part like this in the past. We can now start exploring some of those trade-offs. So after we've added as many materials as we'd like to explore with, we see this green check mark here. That's a pre-check saying that everything has been set up correctly, and the setup has all the information required to run effectively. And even still, before generating, we can also run a local preview. And what this will do is it's taking your geometry, it's taking your loading conditions. You can see this toolbar at the bottom right. It's going to create a very quick local preview within about 15 to 20 seconds, just so you can ensure that everything's been set up correctly. So here you can see this material has been added to the screen. We can see that it's avoiding the obstacle geometries the right way, the way that we might expect. If we wanted to, we could even drag out some of the obstacles on the top here to make sure that we're really clearing out all that material. And when we're happy with the pre-check and we think that this is going to solve effectively, we can close that out and then we can generate this project. So again, all of that we just showed right there was for one specific solve itself. So you can do up to 10 materials in a total of 8 manufacturing options within one solve. So after you generate, and a project like this should take anywhere from 30 minutes to maybe at most a few hours if you have really complicated manufacturing techniques. The next thing is you want to start exploring these options and then finding the ones to move forward with. So we set that one up twice. And after setting that up twice, we have 160 unique validated options that we can then explore. The first thing you might notice is that 141 of these converged, meaning they've met the objectives that we've set. And 19 have completed, meaning that they can't generate any more. There's not any more material that could be added or removed, but they won't meet the specific objectives. And that's actually really interesting to see where materials might actually not be strong enough to do what you need them to do. So it's all very useful information on that sense. So the first thing you'll notice, there's a range of thumbnails for each one of the outcomes, and each one of these is their own unique specific application. You might see things that look really weird like this, and those are pretty much saying that that was a material that we selected that was not strong enough to do what we need. You'll also see these filtering tools on the left side, so we can filter to only show completed, only show the converged solutions. We can say only show me additive manufacturing options or 3-axis. We can also use the objective ranges at the bottom. So let's say I only wanted to look at parts that were less than 3.5 pounds. It's going to filter all of these outcomes that we see on the screen to the objectives that we set on the left. So outside of this thumbnail view, we also can view all the properties for each one of the outcomes, and we can sort them at the top. So here you can see this is saying all the materials. This is a steel. It's meant to be 3-axis milled in all of these orientations. This is the factor of safety target that we had, and it reached that successfully, so it converged. So again, we can also sort that as well. So if we wanted to say, show me the part that has the least amount of material or the lowest volume first, you can see that there. Show me the one that has the least mass first. You can also take several of these outcomes, and if you click on the check mark at the top, you can select up to 4 of them at a time. And then what you can do is you can start to compare these side by side. So you'll see this comparison tab at the bottom right. And as I click that up, it's going to open up all 4 of these within a window. And then you can go through and really start to compare each one of these one-on-one. So then the next thing you might want to do, and this is something that whenever I show this to a team of engineers, this is the thing that they're the most excited about by far, is that you can view each one of these unique outputs graphically as well. So if you click on this third option, you can get a scatter plot view, and you can change the axes to whatever you'd like to explore. And now each point that you see on the screen represents its own unique solution to this problem. So again, this is really the power of this software. It's exploring a range of options. And from here, you can select a window and filter down even further, and then use the objectives to try to narrow that down a little bit more. So let's say we wanted to find a part that was high strength and pretty low mass, and this is one that we'd like to look at. So looking at this outcome, this is telling us that this is an unrestricted solve. So this one is not applying any manufacturing intelligence. This one has met our criteria, and we can also put a stress reference on top of our part. So you can see anything in green is saying that's ideal. The generated geometry has come out ideal. It's not too much material where it's overly strong, and it's not too little where it's too weak. So at the beginning, we talked about generating hundreds or thousands of outputs. And where this really comes into play is that within each one of these outputs, there's also a range of iterations that we can then use. So at the bottom, you'll see this timeline of iterations. And let's say that the final converged solution maybe was too thin, or you didn't need something that was that light. You can start to scale that iteration bar and move further towards the left earlier in the solve to something that might be a little bit heavier, maybe something you're more comfortable with. So again, the idea there being, even though there's 160 unique outputs, within each one of those 160, there's probably also 10 to 50, maybe even 100 specific iterations that you can select on. So we've shown a additive manufacturing, or we've shown an unrestricted solution. So I also want to show a subtractive manufacturing solution as well as an additive one. So if we click on one of these additive solutions, you'll see that the orientation is in the Y positive direction. So this is meaning that it would try to make it self-supporting, moving in the positive Y, which doesn't really make a lot of sense for that output. So we can try to look for one that's positive Z, and we know that that's going to be something that will make sense for a production process. So you can see it's creating geometry that would lay flat on the platform at the bottom, and then it's adding material up to meet that overhang angle that you set to then create geometry that could be self-supporting if it's printing, in this case, in the positive Z. So again, this is very unique from even the other additive example that we showed for this part, and it's very unique from the subtractive results as well. So when you're happy with a solution, and let's say this is the one that you'd like to move forward with, we've talked about this a little bit, where one of the key values within this workflow is that you're generating solid usable CAD geometry on the back end, right? So we're not just creating a mesh that we would then have to resurface or model over. So when you're happy with the iteration you'd like to move forward with, you click on the Export tab at the top, and you can send out a solid CAD output for this model. So when you do that, what you get back is what you're seeing on the screen, right? So you get one solid part for that. And then at the bottom, you'll see a timeline. And what this really is the first thing it does, it brings in our preserved geometries. It then brings in our obstacle geometries. It takes all this generated organic geometry and creates what's called a T-splines model from that. And then it combines them together and subtracts. So at the end, you get all of these solid, crisp lines around the circles that you had created in the first case for the preserved geometries. And then you also have this organic generated geometry connecting them. So it's kind of combining this world of organic modeling with solid parametric modeling. So from here, it's always been really challenging to adjust any kind of organic geometry. It's not something that's really been easy to do in the past, but by combining these two processes, if we wanted to adjust something like this strut that you see on the screen, the only thing that we have to do is roll the timeline towards the T-spline model, select it twice, and that will open up a T-splines environment. We just need to select one of those faces, press Edit Form, apply it locally to that, and then we can automatically select features. So here we automatically select that strut, and just using the points, we can just drag that up and down and scale that to whatever size we'd like. So again, that would be pretty much impossible without using T-splines, and it's a really powerful solution. If you want to get further into it, just please feel free to reach out to me. So if we'd like to scale that up a little bit, we can just drag that surface up, When we're happy with that, we just press Finish Form at the top, and then we can scale our timeline all the way to the right. That's again combining that to that one solid output. So that's really the workflow that we wanted to cover today. So again, setting up the generative project, exploring the options, and then adjusting the outcome CAD geometry is really all that you need to do to successfully run one of these projects. So just a few other notes in closing, and then we should have about 5 minutes for questions. Once again, I would highly recommend using the Fusion Adoption Portal. This is a great way to learn pretty much all the technical workflows that you would need to set up a project and then solve it effectively. If you don't have commercial access to Fusion 360 and cloud credits for generative, please feel free to use the trial that you see on the screen. I will also share this link with everyone as follow-up. And then again, please feel free to reach out to me with any questions or any ideas on how we might be able to help you in your projects. So my email address is there, and I will attach that to the chat window as well. So we have about 5 minutes for Q&A. I wanted to post some of the most frequently asked questions because we do get some questions that come up pretty often. The first one is generative available for education? So not currently. Generative is only available for commercial Fusion 360 subscriptions. If you would like to learn more about that, if you are within the education field, please feel free to reach out to me and we can hopefully try to track something down. Another question that we typically get is how much is one cloud credit? So we've talked about cloud credits for running generative solves. One cloud credit is typically $1 US. Third question, can you trial generative? The answer is yes, absolutely. You can load a trial of Fusion for 30 days and use it on generative projects. We will be recording the webinar. We do have recorded webinars available as well, so you can use these after the presentation today. So with that, I'd like to stop and I'll take a look at the Q&A window and I'll start to answer some of these questions that we see here. So keep the questions coming, and we have about 5 minutes to try to answer as many of these as we can. So the first question from Kevin, when we were setting up the GE bracket, why did we clone the load cases rather than just adding separate force constraints to one load case? So the reason that we've cloned them into multiple load cases is so that all of those forces would not be combined into one sort of ultimate force. So in that case, we knew that this bracket had to be able to hold, in one case, 8,000 pounds in the positive Z. But then in a different case, it also needed to hold negative 8,500 in the Y. So if we combine those within one load case, we're going to have one separate load where we really need to account for two. And that's what the ability of multiple load cases allows us to do. Second question, this one also from Kevin. Would generation always cost 25 regardless of the amount of model size, materials, and manufacturing methods? So that's correct. It always costs the same amount. And the idea there being that even if you only have one material and one manufacturing type, we would like to promote the idea of exploring a range of options. So that's why even if you explored 10 materials and all the manufacturing types, it's going to be the same cost as if you did one. So you might as well explore the entire range if you can. Just skipping around between all these questions, a question from John: are there plans to include a costing feature for the outcomes? 100%. That is something that's very important to us as we start making trade-offs for all the outcomes. Knowing what the cost of each one is obviously a very important part of that. So we are working on having costing eventually. So a question from Jeff: if I want to use FDM and nylon, can I input material strength, stress limitations of the material in a unique axis? So generative is only applying for an isotropic solution, meaning it's the same strength in all orientations. And that's obviously not the case for things like FDM and some other solutions. So what we typically recommend in those cases is that you add the material and you use the weak orientation for the material properties. That way you can have a conservative estimate for the overall, even if it is in the worst printing orientation, you know that you've used the weak orientation properties for the entire part. So another question, when will we see results of generative on mass products? Will it stay in the future as extra cost? So generative in mass products, if I'm understanding the question correctly, um, has been used primarily in the automotive, aerospace, and heavy equipment industries. We have some success in consumer products as well, but it's not very likely that you'll be seeing generative consumer products within the next few months. Again, these are typically heavy duty engineering applications that we see a lot of the early success in. Okay, thank you for everyone that's asked all of these questions. I do have to drop in 1 minute, but I will include my email address in the chat window. If there was something I didn't answer on the call today, please feel free to reach out to me and you can ask that directly. And it looks like no further questions coming in. So once again, thank you for everyone that joined the webinar today. Really appreciate your time. And if you have any questions moving forward, please feel free to reach out to me separately. Thank you.